Good morning, students. Today, what we are going to see we are going to see about a finite impulse response filters. Okay, FIR. We'll be shortly noting as an FIR filters. Okay, so in FIR, we are in need to know how to design the FIR filters. So we'll have often symmetric and anti-symmetric filters. And while we are designing a FIR filters, we'll be using three different methods. One method is to be named as an Fourier series method. The next method is to be our windowing method. Actually, we'll have several types of windowings. So particularly as per our syllabus, we'll be seeing about only often three different windowing methods. One to be the rectangular windowing method, Hamming and Hanning. Okay, and then we'll be seeing about the frequency sampling method. Finally, we are in need to know about how to realize the FIR filter structures. There is a linear phase structure and direct form realizations. So these are all the topics that which have to be seen in FIR impulse response. So now let me say about an introduction of an FIR filters. So when you are saying about an digital filters, it is a filter that operates on the digital signals. There is a filter, a digital filter is a filter that operates on the digital signals. So when we are saying about an types of a digital filters, so we'll have often FIR filters and then IIR filters. So IIR filters that already we are seeing about, second unit, it is infinite impulse response. So here I already said you that we'll having often finite impulse response. So when we are saying over there, actually the digital filter which is designed using finite number of response coefficient. That is, we can able to define the finite value. So impulse response notation remember means of an h of n. So if you are denoting in terms of an finite impulse value, so finite impulse response of coefficient, then that is to be given as some finite impulse response filters. So when we are saying about an advantages, actually it will have a exact linear phase and where the FIR filters are always stable. They can be realized in both recursive and non-recursive structures. We'll have a it is a FIR filters with any arbitrary magnitude response which can be tackled using FIR sequences. When you're saying about the disadvantages, actually for the same filter specification, the order of the filter design will be high as 5 to 10 times that of an IIR filters. And the storage, it will be requiring large storage requirement, and the power computation facilities will be required for the implementation. So these are all the advantages and disadvantages of an FIR filter. So next, let me see about what is linear, what is the condition to derive for the linear phase FIR filters. Actually, it was asked in November, December 2009. Okay. So when you are saying about a transfer function, we know that h of z is equivalent to summation n is equal to 0 to n minus n, h of n is z bar minus n. Okay. So where h of n is to be given as an impulse response of the filter. So we have to take a Fourier transform. So we know that when you are taking a Fourier transform, z will be replaced by e power j omega. So summation n is equal to 0 to n minus n, h of n e power minus j omega. So when we are saying over here, which is to be a periodic with a frequency, periodic in frequency with a period of 2 pi. So we will be replacing our h of e power j omega is equivalent to, that is your modulus of your magnitude response and your phase response. So we will be rotating as an magnitude as an modulus of h of e power j omega and the angle of an e power minus j theta of omega. So we have to define the phase delay and group delay of a filter. So when you are defining a phase delay, that is to be your that is the theta with respect to your omega value, whereas delay is nothing but an differentiation of your value. So when you are saying about for a FIR filters with a linear phase, we can able to define that. Okay. So where alpha to be the constant value, that is minus alpha omega. This is the condition for your linear phase FIR filters, minus alpha omega. So the value will be varying from, omega will vary from minus pi to pi. So alpha to be the constant value and omega to be the phase delay in samples. So let me mark this is to be equation 1 and equation 2. So when you are substituting equation 2 and 1, so what will happen now? So we'll be getting of an summation n is equal to 0 to n minus n, h of n e power minus j omega n which is equivalent to modulus of h of e power j omega, e power minus j theta of omega. So we'll be giving in terms of an cosine value. So this is in terms of an real values, neglecting the imaginary terms. We'll be having in terms of an cos of omega value. Okay. So actually, so we'll be separating real parts and imaginary parts. So real parts we'll be having in terms of an cos value, and imaginary terms we'll be having about a sine value. So by taking the ratio of, let me mark the equation to be on 3 and 4. So we'll be dividing the equation 3 to 4, so that what we'll be obtaining over on it. So summation is equal to 0 to n minus 1 h of n sine of omega n. Similarly, the cos value. So sine by cos, so we'll be getting of our equation over there. Okay. So after simplifying the equation, so what we can able to obtain summation n is equal to 0 to n minus 1 h of n sine of alpha minus n into omega, which is equal to 0. So we are in need to know when the equations can be 0. When, because we have to make a, it is of a multiplication factor h of n into your sine of some values. Okay. So obviously sine can, if we are making sine to be a 0, the entire value will be equal to 0. So when we are equating the value of an h of n is equivalent to h of n minus 1 minus n, where alpha is equivalent to n minus 1 by 2. So if we are making these two conditions, then obviously 50 equations can be equivalent to 0. Okay, so what we can able to conclude now, FIR filters will have a constant phase and group delays when the impulse response is symmetrical about alpha equals to n minus 1 by 2. So actually the impulse response which is satisfying the equations 7 and 8 for odd and even values of n. So suppose for example n is equal to 7. That is if you are taking then odd value. Okay. The center of the symmetry response will be occurring at an third samples. Similarly, when you are saying about an n is equivalent to 6, what will happen filter delay? So 6, the filter delay will be a 2.5 samples. Okay. So if only we'll be requiring about a constant group delay and not the phase delay, abina we'll be replacing of theta of omega is equals to beta minus alpha. So now we have h of e power j omega. So modulus of h of e power j omega into a e power of minus j power j omega. So we'll be remodifying our equation. So that is to be your plus or minus of your angle and your magnitude value. So again, what we'll be having of your, we'll be separating of it. So there is instead of having a theta of omega, we'll be suppose if it is with respect to only a group delay, that is we'll be replacing theta of omega as an beta minus alpha. Okay. So we'll be following up the same steps. That is by separating real terms and their imaginary terms. Instead of having the value of omega, we'll be having as an beta minus alpha of your omega. So when you are separating real terms, cos omega and sin omega, cos of beta minus alpha into omega into sin of beta minus alpha omega. So take a ratio of your equation. So what will happen? So h of n sin of beta minus alpha minus n into omega is equivalent to 0. Okay. So when this equation will become 0, when you are replacing beta is equivalent to pi by 2, so the equations can become 0. Okay. So summation n is equal to 0 to n minus 1 h of n cos of alpha minus n into omega is equivalent to 0. So we'll have a two different case. One to be the sine value. So for the case of sine value, we have to replace beta equivalent to pi by 2. So obviously sine 90 minus theta. So we'll be getting off an. Similarly, in the case of an real value, we have to replace h of n into h of n is equivalent to h of n minus 1 minus n, where alpha is equivalent to n minus 1 by 2. So these are the two conditions we'll be getting off an 0. So when you are saying about so FIR filters, so they will be having of a constant group and not constant phase delay. So what will happen, Abina? Then it is to be named as an anti-symmetrical. So where alpha is equivalent to n minus 1 by 2. Okay. So this is to be the centrometric diagram. So we'll be having often for n is equivalent to 7, alpha is equivalent to n minus 1 by 2. 7 minus 1 by 2 will be equivalent to 3. Okay. So let me have a, we'll be analyzing a linear phase for different cases. So what will happen? we'll have a two response, one to be the symmetrical response, another one to be the asymmetrical response. So symmetrical response we'll be having of an we'll be having of an for the case of an n is equivalent to odd over on it. Similarly, for symmetrical response, n should be even. Similarly, in the case of an antisymmetrical response, we have to consider n is to be odd and n is to be even. So let me have the first one. So let be the question to be like this. Determine the frequency response of FIR filters with symmetric impulse response and the order of the filter n is to be odd. The frequency response, so we know that we can be able to write it as h of e power j omega summation n is equal to 0 to m minus 1 by 2 h of n e power minus j omega plus h of m minus 1 by 2 e power minus j m minus 1 by 2 plus h of n e power minus j omega. Okay. So the thing is to be that we are splitting the equation with respect to our symmetrical response. Okay. So let n is equivalent to, we'll be replacing by means of an m minus 1 minus n. So is that equivalent to your value? So it's equivalent to e power j omega. So after modification, so what will happen? We'll be getting of our second equation to be summation n is equal to 0 to m minus 1 by 2 h of n e power minus j omega. So h of m minus 1 by 2. So similarly, the next response h of m minus 1 minus n. Okay. So for symmetrical impulsive response, so we know that we have to make a condition that h of n is equivalent to h of m minus 1 minus n. So we have to substitute in the relation in above equation 2. So while you are substituting the common factor, what you can able to hit the e power minus j omega m minus 1 by 2. So after taking common value, so we'll be getting often summation is equal to 0 to n minus 1 by 2 h of n e power minus j omega of m minus 1 by 2. Similarly, so we'll have a two factors over on it. So while you are adding of this, we'll be getting often 2 and then plus value. Okay. So the polar value can be represented as like this. Okay. The magnitude and the angle response has to be carried out over it. This is the ways how to define for the case of an odd value. Similarly, when we are defining for an even response value, the frequency response of impulse response, which will be returning as an h of e power j omega, we have to replace n is equivalent to m minus 1 minus n. Then where is it equivalent to, we have to replace. Then again for symmetric impulsive response, we know that h of n is equivalent to h of m minus 1 minus n. So substitute in that relation. So we'll be taking modification as it is. So since we are having the cosine factor, so we'll have a e power minus j omega of m minus 1 by 2 summation n is equivalent to, so 2 factor of value 2 into summation n is equal to 0 to m minus 2 by n h of n cos omega m minus 1 by 2 minus n. So from that equation, we have to write out the magnitude and the polar angle value. Okay. Actually, in the next class, what you should do it of Abina, we have to analyze the antisymmetrical response for n is odd and for n is even. Okay. So for all the types of equations, what we can able to have it of Abina, that is the h of m minus 1 by 2, which is equivalent to 0. Okay. Thank you, students. We'll be seeing on tomorrow.